So we talked about, not only in this lecture, also in previous lectures, we talked about how to, the equations for computing some of these things. In this course, we are not talking about homogeneous reactor type combustion problems. Why? Because there's a kinetics course also, and at least in the past, it was that course is supposed to take care of this. And I know Professor Green here also talks about explosion limits and things like that. So that's why we skipped this. But this is another thing that's interesting to compute. And so I want to show you how to compute this. There were also questions here about how to compute this. So we have developed in the past a code is called FlameMaster. Is a C++ computer code for 0D combustion and 1D laminar flame calculation. So basically, with this code, you can compute anything that is less than two-dimensional. Okay? The code is freely available, and it's an open source code. Okay? Many people use it. It doesn't come with a lot of documentation, but many groups use it. It comes with a lot of examples, so it's relatively easy to do some of these standard calculations. And when you go more into the details, then you know it's relatively easy to use, I think. So it can compute non-premixed and premixed combustion, steady and unsteady. There's an emphasis really on pre and post processing. Sensitivity analysis, reaction flux analysis, and things like that are actually very straightforward to do. So, was there a question? Yes? Does it work on Windows and Linux? The code, I run it on my Mac, OS X. Of course, it runs on all Unix systems. And it also runs on Windows, but you have to install some Unix shell under Windows. I never touched a Windows computer in my life, but my students, I don't know how it operates. All I know is for Windows computer, you have to press the start button when you want to switch it off, right? That's all I know, and then I stopped looking at Windows. So, but some of my students, they have developed a version that it comes with instruction information. Now installing the code sometimes not easy, and if you have problems installing the code, I'm happy to help. You know, if something there's an automatic installation, but sometimes it's very hard. I mean, every computer is different architecture, different compilers, different libraries. Making all of this general is just too much. So we just look at sometimes what's going on. Okay, so I just want to show you here a few examples. This homogeneous reactor at constant volume. This would correspond to a shock tube experiment. You see here simulations for N-octanol. This is a recent paper that we've written on a mechanism here for N-octanol. And then also these are species mass fractions here, for example, here for methyl cyclohexane as a function of time also in these shock tubes. Flow reactor, this would be constant pressure flow reactor like the one that's run also here in Princeton. I think these might be experiments even here from Princeton. This again, methyl cyclohexane, so-called plug flow reactor, and here you see species concentration as function of time. Then this is a jet-stirred reactor. These are experiments here from Professor Dargaud's group in France. And you see here again, I mean, here really you do for each single temperature, you do one calculation, and then you get these things. So typically what the code does, for example, for these here also, for each temperature, you do one calculation, but typically you just say, I want to compute everything from 700 to 1500 Kelvin, and then you just get these, it just does, and you say, I want to do this for these equivalence ratios and for these pressures, and then it's all done automatically. Okay, reaction flux analysis, this was also done with this thing. Here's also methyl cyclohexane. This is a paper that is just under review. If you have it for review, be nice. So there are many different ways of doing post-processing with this. So this graph is not done automatically. That the student or the postdoc did this, but the numbers all you get. Then laminar burning velocities, and again here you would say I want to have the burning velocities for these conditions, and then you get these curves here computed basically at once. What is this here? I don't even remember what the fuel is here. Okay, and this is a premixed flame structure. These are burner stabilized premixed flames like we talked about. You see here mole fraction. Here again is methyl cyclohexane. This is O2 again compared with the experiments. And then we also use this for flamelet libraries. You just saw how we compute these, how we derive these flamelet equations. You can solve these flamelet equations for many different dissipation rates, and then store the solutions in so-called flamelet libraries, and then use that in simulations of turbulent non-premixed combustion. We'll talk about this in the second part. But that also basically is an automatic process that would compute all of these profiles here at the same time automatically. And you see here the arrow is actually in the right direction. And then this here gives you, it's hard to see, but it gives you a variation here of the mixture fraction variance. Again, that's a quantity that we'll introduce in a few minutes. I mentioned this earlier to someone. You can also compute the whole S-shaped curve with this, goes automatically and uses what's called an arc length continuation method. There are several other configurations here, for example, counterflow premixed flames and so on, that I didn't talk here about. But so if you're interested in this, you can go to our website and just click the download button, and then you will get a password. So again, the code is open source, it's for free, and companies have to pay a small license fee, though. But for everyone else, it's for free. Yes?
How is the efficiency of the flame master compared with the Chemkin software?
Just like I never touched Windows, I never touched Chemkin either. I heard people tell me it's much faster, but I don't know if that's true. You should assess this yourself. And maybe it's just true for certain configurations or whatever. I don't know. Did you have a question? No. Okay? Yes?
In terms of kinetics, is there any limitation to number of species, number of elemental reactions?
No, you can, the simulations get slower. You need memory. That's what you need if you have really large mechanisms. Especially when you compute, for example, diffusion flames. For very, very large kinetic mechanisms, that gets very, very slow also. But especially here also these ignition problems, they're very fast. They're really, a matter of seconds, really. Okay? Good. So as I mentioned, single droplet combustion, we'll skip this here. Because it's I don't want to create competition here also for Professor Wright's course. The real point here is how do I, when I think of multiphase combustion, how do I consider multiphase combustion in, for example, these flamelet equations? And it turns out the solution, there's an analytic solution to combustion of a single droplet, and that analytic solution, it gives you a hint for how you could do this. And so that's basically what we do. What this suggests is to, I just tell you what the end result is. What this suggests is if we let's say this would be a temperature profile as function of mixture fraction. And then now, but here the fuel is in the gas phase. But what happens if the fuel is liquid? Then you have, in addition to, so in the evaporation process, you actually need to supply energy to overcome the latent heat. Okay? What the analysis tells you is for the single droplet, you get the same solution, for the whole droplet with evaporation, everything. Or if you assume the droplet is in the gas, is in vapor form, and you use, instead of using the liquid droplet temperature, you use the liquid droplet temperature minus the latent heat divided by Cp. Okay, so this is basically the latent heat divided by Cp. That is a temperature difference that you subtract here, and then you get, under the assumptions, many simplifying assumptions that are made, and then you get the same analytic solutions. Okay, and so we use a similar. So this basically assumes that this is constant and so on, and we use, when we do actual simulations, we use a similar form, which just is a little more accurate and doesn't make any assumptions about constant Cp or whatever. Important to know that this satisfies now the first law of thermodynamics, because you consider that the fuel actually has a lower enthalpy stream than if the fuel was vapor at the same temperature. You consider this, so it satisfies first law of thermodynamics, but it violates, of course, the second law of thermodynamics. Okay, because what you do here is you have a liquid droplet, and now at constant enthalpy, you evaporate it, and the only way then to evaporate is to cool it off at the same time, because the enthalpy has to stay the same. That's what we do here. And that, of course, is something that wouldn't happen. Wouldn't happen in real life. It wouldn't happen if the second law of thermodynamics sheriff was present. Okay. So this is basically what this does, and we're going to skip this here. Okay, so then with this, I could put up this summary slide here, which I want to do, but I don't need to summarize this here. But the point is also, now we're at the end of the first part of this, so exactly 2.5 days, or almost exactly 2.5 days, and we'll move on to the second part. Any questions about these laminar combustion before we move on to the second part?
Some of the plots you showed from these flame mass simulations show that the laminar burning velocity is fastest for rich equivalence ratios, just slightly richer.
Yeah.
Can you comment on why that is?
Yeah, so the question is, why is the burning velocity highest for slightly rich conditions? That's what you saw on these plots. That's very typical for basically all hydrocarbon fuels. That is because the burning velocity depends strongly on the adiabatic flame temperature, and that flame temperature actually it goes up a little bit, and that is because if you think about we talked earlier about, is not the fuel that's left over. You still convert the fuel to CO, and then the CO is left over. So it's not the lean and the rich. They are not exactly the same. Turns out, actually, if you use single-step chemistry, then the burning velocity keeps going up at rich conditions. It doesn't. It goes up. It goes down only at very, very high, equivalence ratio, and the reason is that it doesn't consider it doesn't get the adiabatic flame temperature right. Yeah. Okay. Yes.
We just discussed about the flame-led solution. So how is it different from flame-led library? I thought, flame-led. How do you construct a flame-led library?
Yeah. So the question is how do you construct a flame-led library? I think we'll talk about this in the next part. I should say again. We had this discussion in the break. The flame-led equations they do not assume infinity fast chemistry. They just assume the chemistry is fast enough that the transport in one direction is much faster than the other direction. That's it. Or the gradients in one much faster than in the other. That's it. That's actually given even when you come to this point where extinction happens. But otherwise, we just talked about this is how the structure looks like. The other thing I should mention also, for the counterflow diffusion flame, this transformation actually is exact. There's no assumption. Okay? If you specify the dissipation rate from the counterflow diffusion flame, there's an exact transformation. Okay? No assumption. Now, in a turbulent flow, so in a laminar flow, then you could say, everywhere in the flow field you have one of these flamelets. But in a turbulent flow calculation, you have a distribution of parameters at each point. And so you need to consider that. And that's a part of the flamelet library. I showed you actually what I showed you was a flamelet library, because you need to consider the variance also of mixture fraction, the turbulent variance. But we'll talk about this in the next lecture. Yes?
So for this flamelet equation, first you need to have a flame. So what if you want to compute, for example, the ignition problem?
Ignition problem. Yeah. So again, what we did, we just derived these equations that describe the structure of a flame. And we didn't say how to use this in a CFD model, okay? But if you want to use this to talk about ignition, then you just have to keep the unsteady term. You keep the unsteady term, and it will give you an ignition process. We actually use this model, these equations as they are, with the unsteady term, to model ignition in diesel engines. It's called representative interactive flamelet model, RIF model. But then now we're talking about the next lecture. Yes?
So, is there a radiation model incorporated in this flame master flame?
Yeah, it's a thin gray gas radiation model. Yeah.
So when we are dealing with, so because the literature will say this thin outlook in approximation is not too much accurate. So how does this?
So this here computes laminar flames. Okay, they're usually on a small scale, where this assumption is really, really good. You talk about larger flames where the optical path is so large that you get absorption again, then you have to do something else. But then, that model doesn't do that. Yeah. We also have a diffusion limit, but that also is only locally valid, so it's not so good. Okay, so let me move on then to the next part. So in the second part now, we want to talk about turbulent combustion. So I come to the next lecture. We want to talk about turbulent combustion, and for that, it's important to have the basic notion of what turbulence is, how turbulence is described, how turbulence is modeled, and all these things. I think the cup is leaking. I'm making a big mess. So that's why we have a section here just on turbulence. Again, I mentioned this earlier. This goes very, very in a good pace here through turbulence. This is a course I give in one semester, and so here, it's very short. You should have the same thing, a week-long course on turbulence before you talk about turbulent combustion. But this is what we do. So this is how turbulence looks like, or this is what it does. You have here the fuel. Let's say you have a patch of fuel or jet. Maybe there's a jet here of fuel, and then you have an oxidizer, and then these diffuse into each other. Now, what turbulence does is something like this. You can look at this. People say, well, turbulence is not real eddies, and it is not. I mean, there are no little eddies like this, but you can think of it like this. Helps the understanding. So think of a lot of little vortices or eddies of different sizes and different, speeds, turning speeds, and so on. And you see what this thing does is it mixes fuel and oxidizer. Now, one thing that's important to understand. Forget about the diffusion. Let's say there's no diffusion, okay? So you have look at the equation, momentum equation. You have an advection term, and you have a molecular mixing term, okay? Viscous term, momentum transport, okay? So these two terms, one is what I call diffusion, the other one is what I call advection or whatever, okay? These eddies, they're advection, and here we have diffusion, okay? So forget about diffusion for a second and just think of advection. What if you superpose this and this? What would these things do? They would take a patch of fuel from here and move it over there, and it would take a patch of air from here and move it over here, and it will look like this at the end of the day, okay? Would that stuff burn or not? No, it would not burn, because I said there's no diffusion. I only have fuel, or I only have air, okay? Nothing else. So it would not burn. Think of turbulence, first of all, the turbulent eddies, first of all, of doing nothing else than moving patches of fluid from here to there. They don't create molecular diffusion. For combustion, this is very important, because it burns only if fuel and air are mixed on a molecular level, okay? So what does the turbulence do? The turbulence increases locally the gradients. Okay, that's all it does. It always builds large gradients. And by building large gradients, you could imagine this thing here, it has a large gradient. I mean, this is fuel, this is oxidizer. But you let this go for a little bit, and this interface becomes very smooth, and the gradient is small, and the mixing is very slow. And turbulence just, does this. It takes a patch from here and puts it there, and now I have super high gradients, and now diffusion can be very fast. And then the gradients get small, and then turbulence again comes, takes one patch, moves it from here to there. I have large gradients again, and so on. And it does it not only on one scale. It doesn't have just these large, big eddies that take a big piece from here and put it here. It does this. It takes a big piece from here and puts it here, but then it takes smaller pieces and puts them here, and yet smaller pieces and put them there, and so on. So the mixing is on all the turbulent mixing. Turbulent mixing, again, think of it as not molecular mixing. Turbulent mixing occurs on all scales, and it creates a lot of interface surface here or whatever, and high gradients, and so diffusion becomes very, very fast. That's what turbulence does. Okay, so that just to give you a picture of how turbulence looks like. We'll talk about some characteristics here of turbulence, a statistical description of turbulence. We'll talk about different types of turbulence. We'll talk about, so statistics of turbulence will introduce a mean and a velocity fluctuation, and then we'll talk about how to derive equations for the mean. And other things here. We'll talk about turbulence models, and then we talk about scales of turbulent flows and Kolmogorov hypothesis, and then we talk about a scalar transport equation. At the end, we'll talk a little bit about large eddy simulation. Okay, let me, before I come to this point, or maybe I'll tell you this after this. So this is, turbulence here. This is Osborne-Reynolds, beginning of the last century, having a little pipe flow experiment here. He has a pipe flow. He put a little dye in the pipe flow, and he sees how the dye, it just moves downstream. And then he increased what at the time was not yet known as the Reynolds number. He identified a non-dimensional group that when he increased this, then at some point the dye, it just mixed instantaneously with all the rest, okay? And he called that the critical whatever number, and somebody else probably called it then the Reynolds number. So the Reynolds number now, of course, very important, and there's a critical Reynolds number where things become turbulent, okay? This is how a turbulent flow would look like. Let's say you sit in a jet, you measure a velocity at one point, then you might get something like this. If you have you know, a time-dependent problem, let's say you create a lot of turbulence and then you let it go, then the turbulence will go away after time, then it will maybe look like this. You know, your velocity, and the velocity decays with time, but then your fluctuations around this mean. Characteristics of a turbulent flow is random, okay? You know, I mean, it's random. So this is not deterministic, and really this means you can't predict it. I mean, you cannot predict the exact evolution of this thing because it's a random process, okay? And chaotic, it's always three-dimensional. Turbulence does not exist in 2D, okay? Why? I mean, what we call turbulence doesn't exist in 2D because turbulence depends on something that's called vortex stretching. That's how the energy transfer, turbulent kinetic energy transfer happens, which we'll talk about. If you think of a vortex, you know, it's something that rotates in this direction, maybe. You have a long vortex. That's a 2D kind of construct. If you stretch that, you have to stretch it in the third direction, okay? So that's why this vortex stretching is very important for turbulence dynamics. Vortex stretching only exists in 3 dimensions. Turbulence is always 3-dimensional, okay? Yes?
So modeling turbulence in 2D sounds like a bad idea.
Now, if you want to resolve the turbulence dynamics, then you need to do it in 3D. For example, in large eddy simulation, you want to resolve part of the turbulence dynamics. You cannot do this in 2D. There's no LES in 2D, okay? But we talk about Reynolds averages. You don't want to resolve the turbulence dynamics. You would just solve for the mean flow. You can do that in 2D. You can do it in 1D if you have a 1D problem, okay? If you have a problem that's statistically one-dimensional, I should say. Large Reynolds number, otherwise it doesn't get turbulent, and also it relies on vorticity. The one thing I wanted to mention, why is turbulence important? Most of the combustion devices we have are turbulent. They rely on turbulent combustion. Why is that? Why wouldn't you, isn't it much easier to have a laminar flame?
You don't get a high volumetric output from it, though?
You get a much higher volumetric output. So to assess this, you could say, you can relatively easily show that the mixing rate goes with the turbulence Reynolds number. Turbulence Reynolds number, that would be U prime times LT divided by nu. U prime, that's a characteristic velocity fluctuation. So let's say, you know, is this here, okay? And then LT, that would be the size of the large turbulent eddies. You know, that would be something like this. And the rate of mixing goes with this. And the turbulence Reynolds number is typically at least 100. You know, for much lower turbulence Reynolds number, you don't have turbulence. This means I'm sorry, I should have said, this is the rate of turbulence mixing compared with laminar mixing, okay? This means turbulence mixing is always at least 100 times faster than laminar mixing. And that's important because if you think about it, think of an aircraft engine. An aircraft engine has a combustor, maybe is that long, okay? And now think you have laminar mixing. That combustor, so it's 1 meter, that combustor now would have to be 100 meter long, okay? So your aircraft engine, that's 100 meter long, guess what it wouldn't do? It wouldn't fly, okay, because it's too big. How can you get it in the air? Okay, so an aircraft engine, without turbulence, it wouldn't even work. You wouldn't even get it off the ground, okay? So that's the, and similarly in an internal combustion engine, you couldn't burn fast enough. You could run only at very, very low speed. You would have to have a larger engine or whatever. The engine would have to be totally different. Also the volumetric, the efficiency, I mentioned this earlier, the efficiency depends on the fact that in a spark ignition engine that you have very fast heat release, okay? So if it's all laminar combustion, then you don't get good efficiency. Okay. Good, statistical, so you see it's random and so on, so we need a statistical description. So the first thing we can do is we can define an average velocity. So look at this. You have two different possibilities here. So you see the average here, that would be the straight line. And here also the average would be something like this straight line here. And the question is only how do we define the average? There's one big difference in these two different profiles. This one here is a profile that is statistically stationary. Okay, the mean is stationary. And this here is a profile that's statistically not stationary. Now, if it's statistically stationary, we can get the mean just by doing a time average, a time integration. Okay? However, if it's not statistically stationary, then you cannot do this because delta t always needs to go to infinity. Okay? You cannot do a time average over a short time span. It's not possible. So, what you need to do then is to do something else. This is the so-called ensemble average. Ensemble average means, let's say you're in a jet. Let's say it is statistically stationary. You do a measurement at this point at one time, and then you do a measurement sometime later, and then you take the average of all these individual measurements. Okay? And if you have an unsteady process, like in an internal combustion engine, you would do your experiments 2,500 times, and you always do one measurement, and then you average over these 2,500 different statistically equal realizations. Okay? That's your ensemble average. Ensemble average you can always do. Time average you cannot always do. Okay? So ensemble average is always good. Time average is sometimes easier to think about for some people. I don't know. Good. So what we want to do then, so we have a mean. We have to find the mean. But now the local instantaneous value is different from the mean. And so if you take the difference between the local instantaneous value and the mean, you get the local fluctuation. And the local fluctuations, again, that is the departure here from the mean. And you see that is a time-varying signal, which is sometimes positive and sometimes negative. But it turns out in the mean, that's just how we define the mean. If you take the mean of this fluctuation, it's 0. Okay? So, that is called the Reynolds decomposition. You take the local instantaneous velocity signal and you divide it up into a mean and a fluctuation. You need to define the mean, and then the fluctuation is just given by the difference. So that's what I just said. The average of the mean is 0, of the fluctuation is 0. You can easily try this out yourself by just plugging the definition in here. And then what's interesting here also, let's say you have changes in density. Then you will often, in the governing equations, you always have terms that are a d by dt of rho t or of rho y. Okay, there's always a density. If the density is constant, that doesn't matter. I mean, it just comes out. But if we want to build averages, you always get averages like this: average of rho u. Now, if you decompose these, rho is rho mean plus rho prime, and u is u mean plus u prime, and then you multiply this out. Then you get 4 terms, actually. You get this term, rho mean times u mean, and you get rho prime times u prime. And you also get rho mean times u prime and rho prime times u mean. Rho prime times u mean, if you take the average of this, it's 0 again, because that's just a fluctuating quantity. The average of a fluctuating quantity is 0. But a fluctuation times a fluctuation, that can actually, the average of this, that does not have to be 0. If these two are totally uncorrelated, these variables, then of course, not of course, but then it's 0. But if these are correlated, then it's not 0. Simplest case is take 2 fluctuating variables and take the same variable, u prime times u prime. Okay? So you see u prime, the only reason why u prime mean is 0 is because sometimes positive, sometimes negative. If I take u prime times u prime, that is always positive. Take the mean of that, that's not 0. Okay? So if things are correlated, then the mean of correlated fluctuation is not 0. Okay, so you see, you know, and if you take an average of rho u, you always get 2 terms. That's messy. So there's a different averaging technique. It's called the Favre averaging. And that Favre averaging, it just is defined in a way that you don't get this term. That's all it is. So you say, we write it like this, is we write the mean with a tilde, and then the fluctuation with a prime prime. And, you know, it's defined that rho times u prime prime mean is 0. And so if I plug this in here, then you see if I have to define u tilde as rho times u mean divided by rho mean. If I define it like this, then this quantity is 0, and then averaging this will always give me just 1 term. Okay, so there's a little trick for variable density flows. In combustion, we always have variable density flows. So we always deal with the so-called Favre averaging. Okay, so then also what you compute, if you compute this quantity, you need to keep in mind that really it's this quantity, it's not the velocity averaged, it's the density weighted velocity averaged, okay? But that usually doesn't make a big difference. Okay, so this is the Favre averaging. You can also convert that back into a conventional Reynolds average, and then you get an extra term here. That's not too important. So talk about turbulence. There are certain assumptions that are sometimes made for turbulent flow. In general, take that aircraft engine. You have a very complicated turbulent flow. Sometimes, for the sake of doing analysis, we define certain cases that are a little simplified. And one is this so-called homogeneous turbulence. Homogeneous turbulence means that all the statistics of the turbulence, they are invariant to translation in space. Okay? So if I measure certain statistics of the turbulence here and here, they are the same. Okay? It does not mean that statistics of the u velocity are the same as statistics of the v velocity. Okay? It just means if I measure at this point statistics for the v velocity and the u velocity, then, and I measure this over here, then it should be the same. Okay? Turns out, if that's your requirement, then you can actually allow for velocity gradients. And for gradients in the mean velocity, at least in one direction. And so that's an important feature, and we'll see later on. We see why this is an important feature. This here is a direct numerical simulation of statistically homogeneous turbulent flow. And then the other one, here's isotropic turbulence. So for turbulence theory, isotropic turbulence is very important. Isotropic turbulence now means the turbulence is homogeneous, first of all, so it's invariant under translation in space, but also it's invariant under rotation. And that now really means, first of all, it means at this point all statistics have to be the same as at this point, but it also means that if I look in this direction, I see the same statistics as when I look in this direction, okay? I measure here the velocities, the statistics for the u velocity and the v velocity, okay? And they have to be the same. And they have to be also the same as I measure the velocity statistic in this direction, okay? So that's called isotropic turbulence. It's invariant under rotation. So in all directions has the same statistics. That can only be true if all the mean velocities are 0, first of all. So for isotropic turbulence, all the mean velocities are 0. And secondly, it also means that that this ui uj prime prime for I not equal to j is 0. That is an important term also. We'll see that later on. So isotropic turbulence has two. So this seems like it's overly simplified, first of all. But it has two very important features. First of all, it's very easy to analyze. I mean, the equations that are very complicated, They reduce to very, very simple sets of equations. So for the analysis, it's very nice. And the second is that there are these Kolmogorov hypotheses, which are basically the foundation of the understanding of turbulence today. And these hypotheses, they assume that if you just look at the small scale turbulence, forget about the big scales, the large scales, just look at the small eddies, then the small eddies, they are all isotropic. So if you look at a small region in a turbulent flow, let's say, and you just look at the small scale motion, then that would be isotropic. So that's another one of the very important features. So this here is and then you have turbulent shear flow. This is a turbulent shear flow. This is a evolving shear layer. So here in the bottom, the flow goes from right to left, and here goes from left to right. And then you see, again, you get these larger scales here, larger. So that's what I said earlier. There's no real eddy. You can't see an eddy here in this thing. But what you can see, when we say eddy, what does it really mean? We mean it's a region of some sort of a coherent motion. Okay, that's what we call an eddy. If you look at this, you see regions here of coherent motion. You see that this whole thing here, it seems like, it's one patch that moves together, or this patch here, or also this patch here. And then if you look at smaller scales, you see this thing here looks like it's, or this thing here looks like it moves together, and things like that. So you'll find these patches of coherent motion. You find these in all different scales. This here is just a jet. This, I think, is a two-dimensional jet, actually. This here is a DNS of shear turbulence, and you see this is a very large DNS, actually. And you see, again, you see this is a region here where, the yellow color seems to be brighter, and here it seems to be not so bright. This is the dissipation rate. So here, dissipation is low. Here it's high. You see these larger regions. When you zoom in, then again inside here you see regions where it's low and where it's high. This is kind of how you should look at these individual eddies. This is just another one. Let's skip this. Okay, so we defined a mean flow, and we defined a mean velocity, and so this means now we can also derive equations for the mean velocity. And the way we do this is we have defined an averaging operator. Again, it could be a time average for statistically stationary flow, or it could be an ensemble average, but it's an operator. We can apply that operator just to the governing equations, and then we get an equation for the mean. So you have this is written here for incompressible flow, constant density flow, just to keep things simple. Okay, you could do the exact same thing, then using not the traditional Reynolds averaging, but using the Favre averaging for variable density flows. So continuity equation and the momentum equation, 4 unknowns, 3 velocity, 1 pressure, and it's also 4 equations, so that makes sense. We do the Reynolds decomposition for all 4 unknowns. You plug this in. I plug this in here, and then we average. Okay, so you take the decomposition, you plug it in here, and then you take the average. And you see here for the continuity equation, you get 2 terms, du mean by dx and du prime by dx. So now I take the average of this. I get du mean by dx mean. Okay, the mean of the mean is still the mean. And then I get du prime by dx mean, and that's 0. Why? Because the averaging operator, it commutes with a derivative. Easy to show. Go back to the definition, and you can easily show this. Also, that the mean of the mean is still the mean, also easy to show. Just go back to the definition, and it's easy to show. So this is the continuity equation for the mean flow, and turns out this is the continuity equation here for the fluctuating flow. Okay, so you also get a continuity equation for that. Okay, so this is nice. Now, let's look at so you see already that here we have This thing is linear. It's linear in U. And if things are linear, then the applying the averaging operator will just always give you back the same thing. I mean, it gives you the same equation for the mean form. But at the end of the day, this is what you get. Okay? And you see this now gives you a set of 6 equations for these 6 unknowns. But here's the problem. Now you have a new tensor here. Now this is UI, UJ, UK. This is a 3rd order tensor. Okay? And now this has many unknowns. Okay? So this is a typical problem in moment methods. If you have a moment equation, so this basically the mean, that's like the first moment. If you have an equation for the first moment, it contains other moments. If you derive equations for these, then you get new moments, okay? So the more of these equations you derive, the more unknowns you get. So that's not a good way to proceed. But this also has this, now you see you get correlations with pressure and the velocity, and this also is very complicated. So how do we close this? This just explains all these terms here a little bit. So we need to think about how to close this, okay? But for now, we can derive another equation, which might be helpful, and that is that of the turbulent kinetic energy. The turbulent kinetic energy is the most important quantity to characterize turbulence. You can think of how do I characterize turbulence? And number one, you have turbulent fluctuation, velocity fluctuations, and the energy of these velocity fluctuations. So this would be UI squared, or UI times UI, or U1 times U1 plus U2 times U2 plus U3 times U3 divided by 2, 1/2 of that. That's kinetic energy of the turbulence. And I forgot the primes everywhere. Just put the primes everywhere. But I just said. So not of the mean flow, just of the turbulence. That's a very important quantity. And we can easily now, from the Reynolds stress equation, we can derive an equation here for this turbulent kinetic energy. This is the definition here you see. Because we have an equation for UI, UJ, we can just contract this tensor, set I equal to J in the equation I just showed you, and then you get this equation for the kinetic energy. And that's now interesting to look at this. So we want to look at this before we talk about models for turbulence, for this Reynolds stress tensor. We want to look at the turbulent kinetic energy equation. Why? Because the equation now, it really tells you where does the turbulence come from and where does it go. Okay? So, this tells you what the turbulent kinetic energy is. We can look at the individual terms. So we have a time-dependent term, a convection term. What does that? You have a patch of high turbulent kinetic energy, and the convection term just moves it with the mean flow. With the mean flow, it moves it from here to there. So that's not very complicated. Then you have this here, this thing. This is the Reynolds stress tensor UI UJ times the gradient here of the mean. Turns out that this UI UJ, that's typically negative, and multiply that with a negative sign here, then this is positive. So this is a production term. This is something that produces turbulent kinetic energy. So what it does is it's the interaction of the turbulence with the mean velocity gradients. Or you could also say, if you have velocity gradients, then these velocity gradients, they will lead to turbulence. And you can think of this easily if you have, for example, a jet. The jet has a shear now with the surrounding. And in the shear layer, you start forming these larger vortices, and that is the initiation of turbulence. Okay, so the turbulence. So that's what this term says. The turbulence extracts the energy from the mean flow. Okay, and it needs velocity gradients to do that. Okay, so you have velocity gradients, you will produce turbulence. I said earlier, for this homogeneous turbulence, you can have mean velocity gradients in one direction, and that's important. That's why it's important, because if you have a velocity gradient in this homogeneous turbulence, you still produce turbulence. So there's a configuration where you do produce turbulence. Isotropic turbulence, all the mean velocities are zeros. There's no mean velocity gradient If there's no mean velocity gradient, there's no turbulence. There's no turbulence production. So the turbulence is there, but it goes away after time, okay? There's no new turbulence produced. Then we have this term here. It's not written out now. This is, depends on the gradients of the velocity fluctuations. Let's see if this is written out here. Yeah. So, so this is how this looks like. This is how this looks like. Is duj dxi plus dui dxj times duj dx by dxi. And so this is now a quantity that depends here on the local gradients of the velocity fluctuations, okay? And so what we said earlier is that what the turbulence does is it makes the velocity gradients just higher and higher. And really, it doesn't make the mean velocity gradient higher. It just creates local fluctuations which have higher and higher velocity gradients. So you could look at it like this. Maybe you have a flow here, and this is a velocity profile, and then the turbulence comes and, with an eddy here, and then it looks like this. Now I made the velocity gradient here larger. Then you have yet a smaller eddy here, which makes this then look like this. And then the velocity gradient gets even higher. And the smaller and smaller these fluctuations are, or the eddies are, the higher the gradients become, okay? When you have very strong advection, and the viscosity is very low, okay, then you do all these things. If the viscosity becomes very high, though, the viscous term becomes very large, then you would just smooth these out immediately, okay? You would get rid of all these fluctuations. So that's what happens here is the turbulence starts at these, makes large fluctuations. But for these large fluctuations, now you have the gradients are very small. So this term, the viscous term is very small. Now you have smaller and smaller fluctuations, which makes higher and larger gradients. Larger and larger gradients means at some point, the viscous term, which depends on the gradients, the local gradients, the viscous term in the momentum equation, in the instantaneous momentum equation, becomes larger and larger the smaller the scales become. And at some point, the gradients are so large that the viscous term now becomes important, and diffusion processes become important. Okay, so that's what this term here basically signifies. This is the gradient here of the velocity fluctuation times the gradient of the velocity fluctuation. Velocity fluctuation squared is what this basically is, and so that becomes very large if the scales become very small. And so this is what we call the dissipation term. This converts kinetic energy into heat, okay, into thermal energy. It dissipates out these fluctuations. Now this dissipation term, remember back we defined the scalar dissipation earlier. Remember how that was defined? That was the gradient of mixture fraction squared, okay? Here, this is the gradient of velocity fluctuation squared, okay? So this epsilon, the dissipation rate, the turbulent kinetic energy dissipation rate, that is for the velocity field the same as what the dissipation rate is for the scalar field, okay? So the dissipation rate, it just takes out local fluctuations. Okay, so these are the two most important terms here, the production and, which comes from the mean gradients, and the dissipation, which relies really on these very, very small scales in the flow that have very high gradients. And this is just you could say this is a turbulent transport here. This is just, how the turbulence also transports kinetic energy, from here to there. Okay, so that's the kinetic energy equation and the meaning of these individual terms. This just shows, the budget, what term is important where. Maybe we can just look at this one here. There are basically three terms in this equation: production, dissipation, and distribution by turbulence. It's called diffusion here. Okay, and this is the importance of these terms in the pipe flow. And you see that if you go here closer to the wall, let's say, Not right at the wall, but closer to the wall, then this distribution term here becomes small, and production is equal to dissipation. I hear this is like my undergraduate course. Usually in the graduate courses, people say, hey, time is up. In the undergraduate courses, when the time is up, usually people start, putting stuff away and making a little noise and all that. And at some point, I realized, oh, time is up. So I was just listening to the background noise, and I see time is up. Okay, so let's stop here, and we'll continue with turbulence. Then turbulence modeling, how you model the Reynolds stress tensor tomorrow.